Hey, what's up everybody? This is JJ with Piazza Research, and in today's video we are going to expand on more general physics concepts and using our same scenario of a binary black hole system, which is awesome and cool to work with. In the previous video we computed the velocity of our black holes around their orbit, and we can use this information to better understand the energy of the entire system. And we are specifically going to be looking for the mechanical energy of the system. And so what is the mechanical energy? Mechanical energy, you may have learned or memorized that it's the kinetic energy plus the potential energy of the system. But what does that really mean? Well, we're trying to find the energy associated with the motion of the parts in the system, which is the kinetic energy, as well as their position or location, which is the potential energy, because they're undergoing a gravitational force. And so as we move closer and closer, or the black holes get closer and closer, their potential energy given their position actually decreases, but their motion may or may not increase. And that depends on if there's conservative forces, which is what mechanical energy relies upon if we don't want it to change. If we want to keep it constant, the mechanical energy can only work with conservative forces. And in this case, we can assume that, at least as we compute mechanical energy, that there is only conservative forces acting on this system, such as gravitation. So why don't we go ahead and write down our expression. We know that kinetic energy plus potential energy equals the mechanical energy of the system. And we've derived kinetic energy to be 1/2 times the mass times the velocity squared. And we can use our velocity that we found in the previous part and plug it in here, plus the potential energy, which is just a modification of Newton's universal law of gravitation, which is big G, our two masses squared. That's why we're squaring it. It's our two masses. And the distance to R naught between them. And this is going to equal our mechanical energy. Now, if we use some algebra and plug this guy in, we get 1/2 times the mass times 1/2, or in this case 1/4, because we're squaring the entire term. So we remove the square root, times GM R naught plus, and in fact this should actually be minus, because potential energy of gravitation decreases as this term gets smaller. We need to make this negative, because as the black holes get closer and closer, the potential energy actually decreases due to the gravitational force moving them closer together. And so this equals, or this is subtracting GM squared, big GM squared, over 2 R naught. And this will equal the mechanical energy of the system. And so maybe we can simplify this a bit. We get 1/8 GM squared over R naught minus 1/2 GM squared over R naught equals our mechanical energy. And so we get, multiply this by 4, we get -3/8 GM squared over R naught equals the mechanical energy of our system, given the speed at which, I should say the velocity at which we calculated our black holes to be moving at. And so there you go. That's this energy of our system. The potential energy of the black holes given their position relative to one another. The closer they get, the more that potential energy decreases, given our negative sign in the expression, which is consistent with how we understand the force of gravity to work. And then we also had how fast these guys were moving around their orbit, which was our kinetic energy, the measure or a scalar quantity for how much motion is involved in the system. And then we added them together to get our total energy of that system, given that we are assuming that only non-conservative forces are acting on it. And we might see in the next video and in the next part of this breakdown that we can actually deal with gravitational waves, which are a non-conservative force. And we're going to lose energy due to the release of a gravitational wave. And so we can do some computations there as well. Thank you. See you in the next video.